Alrighty, good afternoon, lads and ladies. Welcome back to Calc 1. Today we are going to continue practice with the fundamental theorem of calculus, and we're also going to talk a little bit, just a little bit, about a new kind of integral. It's not anything really all that new, it's really just new notation. But I want to make sure you guys have everything you need to work on the homework. So yeah, let's get to it. Get the screen share rolling, get our .cam up. The class has thinned pretty dramatically over the last few weeks, and I wanted to also say how grateful I am to you guys for your regular attendance. I know it's a challenge, the era of COVID, for us to be getting up early and doing these meetings. It's not quite the same as doing it in person, and I think your discipline is really going to pay off. And I wanted to let you know that I'm personally grateful that you guys take this seriously and show up. Thank you for this. This, of course, is MAC 1105, sorry, not MAC 1105, MAC 2311, section 002. This is a lecture. Today is the 31st of March, 2021. Today we're going to get more practice with the fundamental theorems, calculus, FTC, and we're going to talk about indefinite integrals. Indefinite integrals, by the way, are section 5.4. So if you've done some research, if you've been trying to read or Google or watch YouTube videos about antiderivatives, probably you've run into these things quite a bit. I know I was working with someone in office hours yesterday, and I was trying to find them some videos, but all of the videos were using this different notation than what we've used to discuss antiderivatives. That notation is the indefinite integral. So following today, you will kind of be on level playing field with everybody else who talks about antiderivatives. And then, of course, more practice with the fundamental theorem is always good. The homework set this week is not small, and I apologize because it was not up until yesterday morning. That was, no, that's my wife. So I do not mind taking a few examples from there to kind of help get you started. Okay, so yeah, homework 11 is up. Showing up yesterday morning. And you see a handful of things that look how you would expect them to look. G of x is the integral from 0 to x of f of t dt, and they just want you to evaluate g at some numbers. This is the same sort of thing we did when discovering FTC1. And they have you talk about mins and maxes for g. So be aware, this is the graph of f. The graph of g, you will want to draw for yourself based on these numbers. All right, so you'll have some points that you can put on the graph of g from these few steps. And that will help you with parts B and C. 2 is the same sort of thing. 3 is the same sort of thing, but with a little bit less help. And those are all things that we've done. But I think it might be nice for us to take a look at a problem or two of this variety and play with it a little bit. So let me take number 5 here. We'll look at him. And then some of these we did the other day. Number 8 we did the other day. But something like number 10, we haven't looked at yet. Number 11, we did that one the other day also. We'll begin with something like number 5. Use the fundamental theorem of calculus part 1 to find the derivative of the function capital F equals integral x to 0, square root of 1 plus secant 4t dt. So I will fiddle with it a little bit. Let's do the square root of, how about 1 minus the tangent of 3. dt. So very, very similar, just swapping a secant for a tangent, basically, swapping a 4 for a 3. So you can follow this if you need help with the problems like problem 5 in the homework. I would love it, though, if somebody could give me a little bit of an idea of where to start or explain a little bit what it is we're going to have to do. Like, what do they mean by this? Use part 1 of the fundamental theorem of calculus. What are they saying? Remind me what FTC1 says. The one that starts if capital F of x equals integral from a up to x of little f of t dt, then what? What's the next bit here? What comes after the then in FTC1?
Isn't it like little f prime of x equals ftc or ft dt?
We're kind of close there. So something happens to the integral. The integral goes away, right? The object whose derivative is referred to, though, is big F. So, right.
Oh, it's like f of, is that a and x?
This is an
Okay,
A.
it's like f prime of a equals or plus f prime of x. Something like that.
So big F primed of x is little f of x. That's what FTC1 says. FTC1 says if big F is the integral from a up to x of little f of t dt, then the derivative of big F is little f. In other words, big F, the function defined in this way, is an antiderivative for little f. But in practice, it tells us how to find the derivative of a function like this. So this is FTC1. And when it comes to theorems like this, we do want to remember them exactly. I know you guys haven't had time to practice with these yet, so I don't expect them to come in all the way. But this process of like struggling to remember, doubting, correcting, that's how we get it baked in. So this is good. This is the statement of the theorem. This is the function I want to differentiate. It looks like the first part of the theorem, right? Capital F of x equals an integral of some shit dt, some shit dt. But there's some pieces here that look different than the corresponding pieces here. So what looks different here? What's wrong with this picture?
X to 0.
Yeah, the integral is being done in the wrong order, right? So how can I fix that?
Can't you just rewrite it as negative 0 to x
Perfect.
of the rest of the function?
Yeah, exactly. We can flip the bounds of a definite integral, and the result is that a negative pops out. The rule here is that the definite integral from a to b, f of t dt, is equal to the negative of the definite integral from b to a, f of t dt. In other words, you can flip the bounds over in an integral, and the result is just that a negative pops out. Okay, so now this is looking more like this, right? Integral from some number, in this case 0, up to x, some function of t dt. So FTC1, capital F prime of X should be equal to what?
Negative square root of 1 minus tan 3x.
Very good. Yeah, perfect. Absolutely perfect, right? The integral goes away. This thing goes in here. Wherever you've got a t, it becomes an x. So this will be negative. That's this negative coming along for the ride. And then the integral goes away, and you're just left with the integrand. That's what we call the function inside the integral, the integrand, which is 1 minus tangent of 3. And then you swap this variable in. Anywhere there is t, there's now an x. Very mechanical, very simple. No need to apply any differentiation rules. No need to evaluate the integral. Nice and straightforward. So FTC1 is like a cheat code for differentiating functions that are defined as integrals. And that's your answer. Boom, done. Not bad, right? Okay. I would like to ask, what would happen if this x was an x squared instead? So then this would be an x squared. What result would that have down here?
Would you put in tangent 3x squared instead?
But there's something else we would have to do also. So
Would we also have to do something with a dt?
there's a way to interpret it like that, but the simplest way to think of this is with the chain rule. So everything kind of goes the same way. The negative would come along for the ride. You'd have the integrand here, the square root of 1 minus the tangent of 3 times whatever is up here, which is x squared. And kind of without thinking, this is what we would get. But if you think a little bit harder, this is really a function, and kind of like this is the outer and this is the inner. Right? It's like I've swapped the inner piece here. The innermost piece here is really this x. That's my variable. This is f of x. X is my variable. I swapped my variable for some function of my variable. So I would need to multiply by the derivative of that inner. Now the derivative of x squared is 2x. So I would get negative 2x square root 1 minus tangent of 3x squared. Like so. And this is as subtle or challenging as FTC1 problems get. All right, if you remember FTC1, just as kind of this basic result, the only way we can modify these to make them harder or deeper or anything like that, that we'll do in this class, is to swap that x for some function of x.
Why isn't the tangent taken out as a derivative? Because it's like derivative of the outside times the derivative of the inside, right?
Well, notice I never differentiated the square root either, right? I never like did any power rule stuff with the square root. The inner function, I say this differently, the integrand here isn't really consequential. We never have to differentiate little f. The idea is that the derivative cancels the integral. So when you take the derivative of a function defined as an integral, the differentiation cancels the integral and you just get the thing inside. Does that make sense?
Yes.
An alternate notation for FTC1, I don't recall off the top of my head if I shared this with you. But an alternate notation for FTC1 using differential operators kind of makes that more clear. Says d dx integral a to x f of t dt equals f of x. So you can kind of see a little bit better what's going on there, that this and this cancel each other out, and you're just left with this piece. Some people even write the dt in front of the f of t here. Physicists, particularly quantum physicists, really like that notation because it kind of lets you think of the integral as one operator, right, rather than like having a dt at the end. But this, I think, highlights a little better the fact that this and this cancel. Really, the dt is a part of the integral. So when those cancel, the only thing that's left is this guy with this variable plugged in. Okay. The main thing we need to be concerned about, though, is learning how to evaluate integrals. FTC1 makes for fun, cute problems like that. But the big skill that we need to be concerned about for the whole rest of the semester is just getting good at evaluating integrals, finding integrals. So let's take a look at one or two problems like that from the homework. Some of these we've done. Let me find something we haven't played with yet. Do something like that. Yeah, I'll modify this again just a little bit. Okay. So I would like to evaluate the integral from 0 to the square root of 3 of 7 over 1 plus x squared. That's how we read this. Where do I even get started with something like this? Kind of, what's my strategy? What should I be trying to do?
The antiderivative.
Good. I want to find an antiderivative for this thing, and then plug in these bounds to that antiderivative. That's what FTC2 says. I have some questions. Is 7 over 1 plus x squared equal to 7 over 1 plus 7 over x squared? Can I do that? No, I can't, right? That's not how fractions add. So this isn't going to help. What about this? Is 7 over 1 plus x squared equal to 7 times 1 over 1 plus x squared? Is that maybe useful? Yeah, this is good. Okay, so that means the integral from 0 up to root 3 of 7 over 1 plus x squared dx is equal to the integral from 0 up to root 3 of 7 times 1 over 1 plus x squared dx. What do I do from here? Yeah, if we recognize an antiderivative right away, we can do that. I would even do one thing before then. I would say this is 7 times the integral from 0 to root 3 of 1 over 1 plus x squared. Yeah, it's because I do know an antiderivative for this piece, and this is a constant multiple. And remember, constant multiples can pop out of integrals. So we've had two suggestions to go for an antiderivative. I think that's a great idea. What is an antiderivative for 1/1 plus x squared?
Arctan.
Very good. The inverse tangent of x. So the 7 comes along for the ride. And then I'll have the evaluation bracket, inverse tangent of x, close evaluation bracket, and write the bounds. The bounds are 0 to √3. Yeah, and you can write this as arctan if you prefer that notation. They mean the same thing. Remember, this is the inverse tangent function. Okay, I need to evaluate this, and this is something I saw on the makeup for exam 2. If you took that, we need to learn a little bit about how to evaluate the inverse tangent function. So this would be the inverse tangent of √3 minus the inverse tangent of 0. What is the inverse tangent of √3 and why?
Wouldn't you just plug in square root of 3 for x?
Yeah, and that's what I've done here, right? So in place of this x, I've plugged in square root of 3. And in place of this x, I've also plugged in 0. That's how we evaluate.
Right. But you would get 1/1 plus square root 3 squared, or 3.
No, remember, that's the derivative of arctan, not arctan itself. This is not arctan. This is the derivative of arctan, or arctan is the antiderivative of this. Arctan is its own function. Graphs help. So here is the graph of 1/1 plus x squared. Here is the graph of arctan. And they're very different.
Right. So sorry. So it would be then, what is tangent when it's equal to 3?
Yeah, so that's the idea. So we need to know what is arctan of √3. So I need to know for what angle theta between
It would be pi/4.
2 and pi/2 is tan theta equal to the square root of 3. Well, the tangent of pi/4 is 1. So here we need some angle so that the tangent of that angle is √3. And that angle has to come from the interval -pi/2 to pi/2. So where is tangent theta equal to √3?
Pi/3.
Yeah, pi/3. And pi/3 is between -pi/2 and pi/2. So this guy, this whole thing here, inverse tangent of √3 is pi/3. What about arctan of 0? What angle between -pi/2 and pi/2 has tangent of that angle equal to 0?
0.
Very good, 0. Tangent of 0 is 0. So the inverse tangent of 0 is 0. So we get 7 times pi/3 minus 0. Or just 7 pi/3. Very good. We don't have an inverse tangent of 1 anywhere. How do we get to inverse tangent? Oh, antiderivative, right? The antiderivative of 1/1 plus x squared is the inverse tangent of x. We know that ddx of inverse tangent of x is 1 over 1 plus x squared. So tan inverse x is an antiderivative for 1 over 1 plus x squared. This is from that table of known antiderivatives. Remember, I gave you guys a kind of two column table the other day. Yeah, this is one of those. There is actually a more general form of this that I'll show you later today, I think. First, any questions on how we did this? Any of the algebra, any of the trig? Okay, let's try one more. Let's evaluate the integral from 0 to pi over 6 of e to the x plus secant x tangent x dx. Now this is a 0 dot here. All right. Thoughts on how we could get started here?
Antiderivatives.
Yeah, these are two things where we can take the antiderivative right away. My only thought here would be maybe to split it up first. But we can jump in right away with our antiderivatives if we want, because the antiderivative plays nice with addition, right? We can kind of think of this and this as their own thing. So what is an antiderivative for e to the x?
E to the x.
Very, very good. And what about secant x tangent x? Who has secant tangent as its derivative? Yeah, Fabrice got
Negative secant?
just secant, just good old fashioned secant. Cosecant cotangent would be negative cosecant. But this guy is going to be just straight up secant. So that is my kind of base or fundamental antiderivative. That is an antiderivative. And I need to put my evaluation between bounds here, 0 to pi over 6. Now, when we do this, we want to think of this thing as a single chunk. We're going to need some parentheses as we evaluate. We're going to plug in the pi over 6 to both of these. And then we're going to subtract from that what we get when we plug in 0 to both of these. So I would write that like this. This is e to the pi over 6 plus the secant of pi over 6 minus e to the 0 plus the secant of 0. And notice that I put each of those instances, this stuff and this stuff, in their own parentheses. Without that, this negative won't distribute and things will come out incorrect. E to the pi over 6 is just e to the pi over 6. There's really nothing we can do with that. But the secant of pi over 6 we should know. What is the secant of pi over 6?
2?
See, it might be, I think so. What is the cosine of pi over 6? We know this is the reciprocal of cosine, right?
Oh, I had those mixed up. It's cosine is 3 pi or square root of 3 over 2.
Very good. So the secant of, if the cosine of pi over 6 is root 3 over 2, then the secant of pi over 6 would be
Root 2 over 3.
2 over root 3. So you just flip it over. You don't have to do anything weird with the square root. So the reciprocal of root 3 over 2 is 2 over root 3. And then here I'll have minus e to the 0, that's 1, plus, what is the secant of 0? Same sort of logic. First, let's find the cosine of 0. What is the cosine of 0?
1.
1.
Mhm. And what's the reciprocal of 1?
1.
Very good. So I have e to the pi over 6 plus 2 over the square root of 3 minus parentheses 1 plus 1, which is minus 2. And that's it. Not too bad, right?
Why is it always like minus?
So this is coming from FTC2. Remember that FTC2, the thing that we're using here, says that the integral from a to b of little f of x dx is equal to capital F of b minus capital F of a, where capital F is an antiderivative. Is any antiderivative. For little f. One way to think of this, kind of if you remember the way we discovered FTC2, is that capital F of b would be the area under little f from 0 up to b. And capital F of a would be the area under little f from 0 up to a. So if you want the area between a and b, you start with all the area up to b, and then you subtract out the area up to a, and that will leave you just with the area between a and b, which is what we're looking for here. That was kind of how we saw it. Remember the triangles, the purple triangle and the blue triangle? Cool, cool. All right. There's a cute joke about integration. See if I can find this. Yeah, here we are. So integration begins feeling like it's not too bad, right? We're getting there. We're getting there. This joke, I enjoy this. I share this with my Calc 2 class at the beginning of the semester because they're worrying about this. So differentiation is not too bad. You know, you get started, you apply whatever the appropriate rule is. And if you're done, yay. If not, then you're going to go back and like more chain rule, more whatever. Integration. You're gonna try some shit and no, it's gonna be a little tougher. Oh, okay, I don't know what to do. I'm gonna do some of this. Fuck, partial fraction Mathematica, maybe computer program Stokes theorem. Call some mathematicians, cry, burn the evidence, and yeah, that's generally integration is much harder. So we're going to warm up like this, but I just want to caution you that this is a skill that is going to take some time to build, and that what we're doing right now is the very, very, very base of that. It's the foundation. So especially if you intend to take Calc 2 after this, we need to lay these foundations in strongly. In particular, that table of antiderivatives needs to be known well. And what we're going to do now is discuss antiderivatives a little bit more because they're the main tool we need to do definite integrals. But we're going to discuss them in the context of a new notation. So an indefinite integral kind of sounds like a not definite integral, right? Definite integrals are the things we just worked on. Indefinite integrals are like another version of an integral that is somehow not definite. It's still an integral, but it's an indefinite one. Basically, it's just notation. Just a new notation for the most general antiderivative. That's it. So here's the notation. If f of x is an antiderivative for little f, then the integral without any bounds, this is what we call the indefinite integral of f, is equal to capital F of x plus c, where c is an arbitrary constant. And what we mean by arbitrary here is I don't care what it is. I'm not worried about c being any particular number. It's just understood that c is a constant. Could be anything. And in fact, what we think of is kind of this as an infinite family of functions. It's all the functions of the form capital F of x plus c, where capital F is the antiderivative you found, and c is allowed to be any constant. So a quick note. Integral a to b of f of x dx, this is a number, right? It's the signed area bounded by f of x from x equals a to x equals b. That's the object we've been playing with. But integral without the a to b of f of x dx, this is an infinite family of functions. That's the set of all antiderivatives, or the collection of all antiderivatives. For little f. So they're very different animals, right? They're just different things. Definite integrals are numbers. Indefinite integrals are infinite families of functions. So while the notation is very, very similar, and the procedure is quite similar, right? Both of these involve finding an antiderivative. This guy turns out to just be a different animal because you never plug in bounds. You never evaluate at the end. You just find that antiderivative and slap on a plus c. Whereas the definite integral, after you find your antiderivative, you never write a plus c. We don't care about the most general antiderivative for definite integrals. We just want to find any antiderivative, and then we plug in those numbers a and b and subtract. So subtle differences between these things, notation wise, but big difference between these things in terms of like what they are. Now, the net change theorem, I don't like that they group these together because they're really nothing to do with each other. But here is this list of indefinite integrals that you guys need to know. And it's the same as the list of antiderivatives. The indefinite integral obeys the same rules as the definite integral. It is linear. But let me go ahead and write these down for you. First, the indefinite integral, just like the definite integral, satisfies the linearity conditions. That if you have a sum of two functions inside an indefinite integral, you can split that up as integral f of x dx plus integral g of x dx. It's easy to get in the habit of not writing the dx, but please don't do that. The dx's are important. I'll explain why in section 5.5. But remember, in terms of Riemann sums, the dx kind of stands for a little width. Even in the indefinite integral, where we're not talking about an area, the dx has a clear and distinct meaning that will become clear. Constants pop out. All right, so these two together form the linearity condition. And then you can think of there as being a whole bunch of, they're not really rules, but antiderivatives we should know, or indefinite integrals we should know. So I'll put these on a separate page here. I guess we start with the integral of a constant. The integral of any constant is just k times x plus c. All right, because who differentiates to a constant? Well, that number times x differentiates that. Like the derivative of 2x is 2, the derivative of pi x is pi, the derivative of 1/2 x is 1/2. So the integral of 2 is 2x. The integral of pi is pi x, and the integral of 1/2 is 1/2 x. And we always slap on our plus c. And then if you're dealing with a power function, x to the n, when we talked about antiderivatives, we said to find an antiderivative for something like this, you increase the power by 1 and you divide by that new power. So you get 1 over n plus 1 times x to the n plus 1 plus c. And this is for all n's except -1. In the case where n is -1, the thing you're integrating there is really 1 over x dx. And here we said that our antiderivative is the natural log of the absolute value of x plus c. Oops, sorry, my wife's calling me. Can you hold your name? All right. And then there's a boatload of other ones, e to the x sine x, all the known trig stuff. I'll go ahead and write these down. integral e to the x dx is e to the x plus c. Integral of some other base exponential b to the x dx is 1 over the natural log of b times b to the x plus c. That's all the exponential stuff you need to know. Trig stuff. Every derivative we know is just read backwards as an antiderivative. So the integral of cos x dx would be sine of x plus a constant. The integral of sine x dx is negative cos x plus a constant. Integral of secant squared x dx, whose derivative is secant squared?
Tan.
Very good, tangent. Hey baby, what's up? I am teaching right now. Yeah, you all right? I'm sorry, baby. Give me a little bit to wrap this up. Yeah, I'll give you a call back, okay? Bye. Love you. All right. While we're here, the integral of cosecant squared. What would that be? Whose derivative is cosecant squared?
Would it be negative cotangent?
Yeah, very good. All right, the derivative of cotangent is negative cosecant squared. So the derivative of negative cotangent is positive cosecant squared. And you can see how this is going. Every derivative formula we know has a counterpart as an integral. It is important that you get these into your notes, so we'll go ahead and complete this table. Secant tangent. Integral of secant x tangent x dx is going to be secant x plus c. The integral of cosecant x cotangent x dx is negative cosecant x plus c. And that's all the crucial trig stuff. The integrals of tangent and cotangent, the integrals of secant and cosecant on their own are quite tricky. I will show you some of those. I won't get all of them, but we need another method before we can get there. They're not considered basic antiderivatives. However, there are a few others that are considered basic that involve inverse trig functions. And one of them we use today, the integral of 1 over 1 plus x squared dx. This is the inverse tangent of x plus c. And then the last one like that is the integral of 1 over the square root of 1 minus x squared. Does anybody remember this? Whose derivative is 1 over root 1 minus x squared?
Inverse sine.
Very good, inverse sine. So this is the same as the table of antiderivatives we had before. Exact same stuff, just written in the integral notation. And these are things that we do need to know. I think you guys could come up with any of these given some time just by thinking about them. This is the one that people tend to forget, this and the two inverse trig things at the bottom. And they can both show up in various problems. They're important. So make sure you hold on to these. One of your homework problems, actually, no, I don't think I put that in there. Yeah, no. But you will see things like this from time to time, like integral of 2 to the x or integral of 5 to the x. That would be like 1 over the natural log of 2 times 2 to the x, or 1 over the natural log of 5 times 5 to the x. Yeah, that's it. So the other thing that shows up in 5.4 is this business of net change. The hyperbolic sines and cosines you don't need to worry about. We don't do hyperbolic trig here at Santa Fe. I guess we could practice a little bit more with those. Yeah, we've done these. Hmm. Okay. It's not really what we were going to talk about. It's not really connected to this, but let's do one more example of an indefinite integral. And let's make it fun. All right, just to be silly. Lots of square roots of 2. So I've got x raised to the power of root 2 over x squared, and e raised to the root 2. And we should think about how to evaluate antiderivatives for each of these. They each require their own sort of thing. We can begin by splitting this up, and I would suggest doing that. So this is integral of x to the root 2 dx plus integral of root 2 over x squared dx plus integral of e to the root 2 dx. Which one of those rules will I apply for the first integral?
The power one.
Yeah, this is x being raised to some power. This is x to the n, where n is root 2. So this first guy is going to give me x to the root 2 plus 1 divided by, or you can write it as 1 over root 2 plus 1, or you can write it down here, divided by root 2 plus 1. And I'll write plus C1 for his constant. And then we still have these other two. This is integral of, I'll write it as root 2 times 1 over x squared dx plus integral of e to the root 2 dx. How do I handle the middle guy? What can I do for this? I can pop this root 2 off the top. Same thing we did with the 7 on that first example. But what can I do here?
The root 2 is a constant.
Good, this is a constant multiple, so he can come out of plus root 2 times the integral of, how do I handle 1 over x squared?
Couldn't you rewrite that as x to the -2 and then use the
Excellent.
power rule?
Very good. So this is another power rule thing. And then over here, I also have this integral. I'll just copy him down for now. Yeah, so the trick to integrating 1 over x squared is to write it as x to the -2. So now I can apply the power rule to this piece, right? What will I get then?
Negative 2x minus to the -1.
Almost. So remember, we need to increase the power by 1 and then divide by that new power. So if I increase the power by 1, I add 1 to -2. I'll get x to the -1. And then, like Mackenzie said, we'll divide by the -1. And so now I've taken my antiderivative there. When the integral goes away, that's when you should write your plus c. I'll write plus c2. And I claim that we can go ahead and do this third integral in this step here also. How do I integrate? Ooh, I wrote e to the square root of x. Sorry, that should be e to the square root of 2. E to the root 2, e to the root 2. What kind of animal is e to the root 2?
E to the root 2.
For sure.
Isn't it a constant raised to a constant?
It is, and that's the sneaky thing here. No,
So you could just pop that out, right?
we could. E is a constant and root 2 is a constant. There's no x's anywhere in here. So e to the square root of 2 is itself constant. And what's the integral of a constant function?
Of that times x. Or the constant times x.
So here we'll get e to the root 2 times x like this. I'll write plus c3. This is subtle, right? The temptation is to say integral of e to the x is e to the x. So integral of e to the root 2 is e to the root 2. It's a very understandable thing to want to do, but it's not correct. Because this isn't e to the x. There are no variables in here anywhere. This is just e to the root 2. It's just a number. It's like 3 raised to the 1.4. It's just a number. So it's just a constant. And the antiderivative of a constant is that constant times x. And now we can clean this up quite a bit. Root 2 plus 1, there's not much we can do there. All right, that's not the same as root 3. The 2 is under a square root, the 1 is not. So this first piece is pretty much stuck. He's going to stay x raised to the root 2 plus 1 divided by root 2 plus 1. The c's I'm going to gather at the end. Then we'll have plus x to the negative 1 divided by negative 1 is negative 1 over x. So this is square root of 2 times negative 1 over x. It's 1 over negative x, but then that negative can come out front. And then this third piece is just e to the root 2 times x. And then over here I have plus c1, plus c2, plus c3. Each one of those had their own constant. But c1, c2, and c3 are arbitrary constants. So we could group these together into a single big plus c. Right? 3 arbitrary constants, 1 arbitrary constant. If they're added up, it doesn't matter. So my final answer here would look like this. X raised to the power of root 2 plus 1 over root 2 plus 1 minus root 2 over x plus e to the root 2 times x like this. The x is not in the power. Plus I would group those 3 together into a single guy. I would call all these together just c. And this would be my final answer here. Little bit sneaky. These sort of problems are commonplace. Each one of these little integrals was something that we know from our table. Just slightly funky looking. So your strongest tool right now is really algebra, is really looking at this thing and recognizing what each of those pieces are and how they can be written in a way that lets you use your table. Questions on this guy? The last little thing in 5.4 is what's called the net change theorem, and I want to address that. Do we have time to talk about that now, or does that need to wait? We got time. It really shouldn't even be called a theorem. It's just kind of an obvious thing. But we'll write it in this notation. So the definite integral, whoop, come here. From x equals a to x equals b of f primed of x is the net change in f of x from x equals a to x equals b. It's really just a restatement of FTC2, i.e. the integral from a to b of f primed of x dx. By FTC2, we would need to find an antiderivative for f primed and then evaluate from b to a. Well, an antiderivative for f primed is f itself. So this is f of b minus f of a. And you recognize from your algebra classes of yore that this is the thing we call, this is the thing we call the net change. Hey, baby, what's up? No. Quarter till. Are you all right? It'll be okay. We'll figure it out. Don't worry, baby. It's gonna be okay. All right, I'll call you. Okay. So remember what we mean by net change, right? It's how far did the function end up compared to where the function started, right? So the net change on an interval a, b, or the net change from x equals a to x equals b is just f of b minus f of a. It's the total vertical distance traveled by the function f. Like this. From a to b. It can be negative, it can be positive, it can be 0. So if b is right here, then this is the point b comma f of b. If a is over here, then this is the point a comma f of a. And the vertical distance between those 2 points f of b. This would be f of a. The vertical distance between these 2 points is the net change. So if your function ends at the same height it started at, then your net change is 0. If your function ends above the point it started at, then your net change is positive, like it would be here. And if your function ended below where it started, if the height over here was lower than the height over here, then your net change would be negative. This is mostly useful in application problems. The graph here is f of x. This is the x-axis. That's the idea. A few important, one particularly important guy here is kinematics, physics stuff. So we know that if position is x of t, velocity is v of t, and acceleration is a of t, then x primed is your velocity, and v primed or x double primed is your acceleration. What this means is that if you integrate velocity, integral from time t equals a to t equals b of your velocity is equal to the integral from time t equals a to t equals b of x primed of t dt would be x of b minus x of a. It's the net change in your position. This is called the displacement. Is the total displacement from time t equals a to t equals b. We actually talked about this way back in section 5.1. We just didn't have the notation to write it as this back then. So there's nothing special here. If you integrate velocity, you get distance. The catch is if your velocity is sometimes negative, the thing you're going to get out isn't necessarily the distance traveled, it's the displacement. So I want to make clear the two differences, the differences between these things. How are we doing on time? We got 6 minutes. I think the example I used when we talked about this was before was walking to the grocery store, right? If I walk to the grocery store and back, my displacement is 0 because I land back where I started. My net displacement is 0 because I finish where I began. But the distance I travel is certainly not 0. And it would be nice if we had a tool for distance traveled. And there is. Similarly, the integral from a to b of the absolute value of v of t dt, which would be the integral from a to b of the absolute value of x primed of t dt. This is equal to the distance traveled. From time t equals a to t equals b. And in practice, integrating absolute value functions can be a little bit tricky because they are not a part of our table. So let's imagine we have the velocity function graphed below. I start out at velocity 0. I'm walking to the grocery store. You know, I'm walking at a steady speed. I get to the grocery store. I realize I forgot my wallet. I turn around and I walk home. And then I stop when I get home. So here is my velocity function, v of t. And maybe this is like, maybe it's like a 5-minute walk. Let's say t equals 5 minutes. And it's like another 5 minutes to get home. So this is 10 minutes. And that the area here say the area here is like 500. Oh. Yeah, why not 500? We'll think of it like it's feet. And the area here is like 500. Everywhere my velocity is positive, I'm walking away from home. Everywhere my velocity is negative, I'm walking back towards home. So the integral from 0 to 5 of v of t dt would be the distance I walk to the grocery store, and that would be 500. The integral from 5 to 10 of v of t dt, what would this be?
$500.
It's tempting to say 500, but remember the integral measures the signed area. So if this area down here is 500, but it's below the x-axis.
Negative 500.
Yeah, negative 500. This would represent me walking 500 feet towards the grocery store. And this would represent me walking 500 feet away from the grocery store, back in the other direction. The integral from 0 to 10 of v of t dt would be what? This is the whole thing. It's not going to be 1,000, not this one. One of the questions I'm gonna ask will be like, yeah, this one's going to be 0, right? I have a positive 500 from this and a negative 500 from this. They cancel perfectly. So this would be 0. And this is my net displacement over the whole trip. So right, I walk to the grocery store, I realize I forgot my wallet, I turn around and walk back. My displacement is 0. I end up where I started. If I wanted the distance, then that would be the integral of the absolute value of v of t dt. And the graph of that absolute value of v of t would look like this instead. It wouldn't have this down here. The absolute value would flip up any negative part of this graph and make it positive. So what's this one?
1,000.
Yeah, this one's 1,000. And this is the distance traveled. So maybe I'll come in here in purple and so the black here is V of t, and the purple in here is the graph of the absolute value of V of t. So to get the distance traveled, you need to integrate the absolute value. If your velocity is always positive, then it's not something you need to worry about. But if your velocity is sometimes positive and sometimes negative, then there is a big difference between the two. Displacement and distance traveled, integral of the regular velocity function versus integral of the absolute value of the velocity function. In practice, how do we do this? In practice, if you're given a function and you need to find the distance traveled, you're given the velocity function, you need to find the distance traveled, what you need to do is figure out what parts of the area are positive and what parts of the area are negative. What's above the x-axis and or the t-axis and what's below the t-axis. There's an explicit example in here. I'd like you guys to take a look at this example. It's example 6 in section 5.4. Since we're out of time now, we're not going to do it now, but we'll begin class on Friday with this example. So please read section 5.4. It's not a hard section to read, but this last bit here where they talk about applications of the net change theorem to physical situations, this is something that warrants your attention. It is not entirely obvious and it will take a little bit of thinking. And then we'll come in, we'll work example 6 and maybe one more of these on Friday, okay? Alrighty, gang. Thank you for coming today. As always, I really do appreciate your continued perseverance in this class. And I will see everybody next time. If you need to talk, of course, you can come by, see me in office hours.
Thank you.
Bye, guys.